All right, let's jump right in. Have you ever wondered how scientists can tell with absolute certainty what's in your food, your water, or even your blood? Well, today we're going to pull back the curtain on the incredible analytical instruments that are basically the ultimate detectives of the chemistry world.
It always starts with a big question, right? Something like this. How in the world do you find a single tiny trace of a banned substance in an athlete's blood sample? Or maybe a dangerous pollutant in an entire city's drinking water? We're talking about amounts so small, it's like trying to find one specific grain of sand on an entire beach. Well, the answer comes down to solving a fundamental two-part puzzle that every one of these machines is built for. First, you have to take a super complex mixture and somehow separate every single ingredient. And second, you have to figure out exactly what each of those ingredients is.
So let's tackle that first step, separating the mixture. And honestly, the best way to think about it is to imagine a great chemical race. Now, the official name for this race is chromatography, and the idea behind it is actually pretty simple. Imagine a racetrack, but in chemistry, we call it the stationary material. When you shoot a mixture of chemicals through it, some of them are going to be stickier and cling to the track, moving really slowly. Others, they'll just zip right through. And that difference in speed is what separates them out perfectly. It's really just a three-step dance. First, you inject your sample, your mixture, into the system. Second, all the different components start to separate as they travel down this long, super thin tube called a column. That's our racetrack. And finally, there's a detector sitting at the finish line that sees each component as it crosses, one by one. Now, there are two main kinds of these racetracks. For stuff that turns into a gas really easily, think about the smell of your coffee. We use what's called gas chromatography, or GC. But for the huge majority of compounds, we're talking over 80% of them, things like vitamins or medicines that might be a bit more sensitive, we use high-performance liquid chromatography, or HPLC. And just like the name says, it uses a liquid instead of a gas to push everything along.
Okay, so we've separated all our chemicals. They finished the race, but we still don't know what they are. And that, my friends, brings us to step 2, revealing their chemical fingerprints. For this part, we bring in a real powerhouse called mass spectrometry, or MS. You can think of it as a molecular scale, but on steroids. It is incredibly precise. It weighs each individual molecule, which gives it a unique mass fingerprint that helps us know exactly what it is.
And how it works is just brilliantly clever. First, as the molecules come off our racetrack, we zap them with electricity to give them a charge. We ionize them. Then we send them flying through a magnetic field. Because they've got that charge, the magnet can now push them around, and it sorts them by their mass. See, the heavier ions are harder to push, so they barely curve. The lighter ones, they get whipped around pretty easily. Finally, a detector at the other end just counts how many ions of each specific mass hit the target. The result is a perfect, unique fingerprint for that molecule. But this is where things get really, really powerful. What do you think happens when you put these two amazing techniques together? Well, you get the ultimate detective duo. That's right. By connecting our separation racetrack, the GC or the LC, directly to our fingerprinting machine, the mass spec, we get something that is pretty close to absolute certainty. The first machine separates, the second one identifies. It's a perfect partnership. And this just shows you how much of a difference that makes. You see, with chromatography alone, you're just identifying something based on the time it took to finish the race. It's a decent guess. If you use mass spec on a messy, unseparated sample, you just get a jumble of fingerprints all on top of each other. Useless. But when you use them together? Oh yeah. Each separated chemical gets its own individual fingerprint scan. You get the race time and the fingerprint. Case closed. And this is what the final report from our detectives looks like. It's so clean. The instrument tells you, hey, at 5.4 minutes, the thing that came out was caffeine, and it weighed 194. A little later, at 8.1 minutes, here comes ibuprofen with a weight of 206. It's clear, it's precise, there's no arguing with it. Now, our detective duo is the star of the show, for sure. But the lab has a whole crew of other specialists, tools that are designed to answer very different, very specific questions. So what if you don't care about the whole molecule and you just want to find individual elements, like lead or mercury in your water? For that, you need a different set of tools. Atomic absorption, or AAS, is like a sniper rifle. It's unbelievably good at finding one specific element. But if you need to do a broad search, you bring out the big guns, ICP-MS. This thing is a beast. It can scan for over 60 different elements at the same time with sensitivity that is just mind-blowing. We're talking parts per trillion. That is like finding a single second in almost 32,000 years. And what about solid stuff? Say you have an unknown white powder. X-ray diffraction, or XRD, can tell you exactly how its atoms are stacked together to form a crystal. That unique pattern is a dead giveaway for whether it's salt, sugar, or something much worse. Then there's infrared spectroscopy, or IR. It asks a totally different question. It doesn't care about the big picture structure. It cares about the individual building blocks, the chemical bonds that make up the molecule. It's like identifying the specific Lego bricks used to build the thing.
So let's put it all together in a quick cheat sheet. This is your analytical toolkit. You've got chromatography, the racetrack, to separate things. You've got spectrometry, the fingerprint, to identify things. Combine them and you get the detective duo. And for just the elements, you've got your element counters. Every tool has a very specific job to do in solving the chemical puzzle.
So why does any of this invisible science matter? I mean, who cares? Well, you do, because these instruments are the silent guardians of our modern world. They are working around the clock, behind the scenes, making sure our food is safe, our medicine is pure, and our environment is healthy. They find the problems long before those problems can find us. And that kind of leaves you with a final thought. The air you're breathing, the water you're drinking, that coffee on your desk, it's all an incredibly complex mixture of chemicals. So what invisible puzzles are hiding in plain sight all around you, just waiting for a detective to come along and solve them?